Hello and welcome to this next video in topic 2. We're here in part 5 where we're looking, or continuing to look actually, at a special case, the QtoQ case. So in the previous video we talked about this case and some really basics. Here we're going to extend those ideas a little bit further. We said originally that this is a somewhat unique case with some interesting tools, and so we're going to explore that here in this particular part of our topic. In this part of the topic, we're going to be careful. We need to restrict our attention to a very special case of relationships that have a linear form. We saw in the previous video that the form of a relationship might be linear. It could be curvilinear. There could be clusters, but we need to be very careful that we keep in mind here that we're only looking at linear relationships. And what we want to do is explore how to measure the strength of the relationship when we have a linear form. So we need to be really careful here. The tools and the measure that we develop here can only be applied to linear relationships. They don't apply to curvilinear, and we need to keep in mind that all relationships are not linear. So this is actually a pretty common mistake that students make when they first encounter this idea. They apply these ideas to non-linear relationships, and that gets you into some trouble, as we're going to show here in a minute with some examples. For example, which relationship here is stronger? Both of them are linear, so we can see they both roughly follow a line. Both of them are positive in terms of their direction, so they're both exhibiting the behavior that as x increases, y increases. So the question here is, how are we going to numerically measure that strength of relationship? Which one is stronger? If you looked at these and you had to guess, which one would you say is stronger? Just look at them. It just so happens that they have the same strength. What's fooling us here is the scale which we're using to illustrate the scatter plots. So this is actually the same data set, except for the fact that you have a different scale on the x and the y axes, and that's fooling us into believing that the strength of the relationship might be different. Here it looks like this one might be stronger than this one, but in fact they are actually of the same strength. So we need a numerical measure so that we're not fooled by things like this, and we can very accurately measure what the strength of a relationship is. The way we do that is with what we call the correlation coefficient, denoted by the letter R. Our definition says that the correlation coefficient is a numerical measure that tells us what the strength and the direction of a linear relationship is between two variables. So it's actually telling us two things, both strength and direction. Now, there are some pretty complicated ways that we use to calculate this value. You can see here's the formula for R, and it's quite complex. We have n here for sample size. We have values for x bar, the mean, individual values of x, and then we've got this capital X, capital S, which we haven't really talked about. And it turns out that even this calculation right here is somewhat complex. So we're not going to worry about how to apply this formula. Instead, we're going to focus on this idea that R tells us the strength and the direction of a relationship, and we're going to rely on technology to give us the value of R for a given data set. What's important here is that we know how to interpret R. So let's talk through that. First of all, the value of the correlation coefficient R will range from between -1 to +1. The direction of the linear relationship is given by the sign of the value of R. So if R is negative, then it implies a negative direction, and if R is positive, it implies a positive direction. That's very convenient. So positive is increasing and negative is decreasing. Values of R that are close to 0 are going to indicate a relatively weak relationship compared to values of R that are closer to either 1 or -1. Now we don't have a hard and fast rule or cutoff for what value of R is weak versus moderate versus strong, but what we do know is that the closer you are to 0, the weaker the relationship, and the further you get towards either 1 or -1 in either direction, you have a stronger relationship. This last bullet illustrates what we just said. If we want a stronger relationship, we're looking for R values that are closer to 1 or -1. In other words, they should be larger in absolute value. So let's suppose we take an example here to illustrate these ideas. A statistics department tracks the progress of students from entry until graduation. So the scenario here is a college. It has a stats department and is trying to figure out how students do from the point where they enter the college or university until they graduate. And the department tabulates the performance of several students in an introductory course and in an upper level course that's required for graduation. And let's suppose you look at the relationship between these two values. So here, as our explanatory variable, we have the average score in the introductory course. And over here as the response variable on the y-axis, we have the average score in the upper level course. So we could say, right, what is the form, the direction, and the strength here? Okay, so the form is either positive or negative. The form is the basic shape that the data take, and you can see here that the basic form is linear. The direction is going to tell us whether or not we're increasing or decreasing, or whether or not it's positive or negative. Remember, increasing relationship corresponds to a positive relationship, and decreasing is negative. So clearly, as one variable, the intro course average increases, the other variable goes up, and so that's an increasing or a positive direction. And then the strength here, using the formula that we saw previously on a previous slide, is 0.931. So this is telling us that we have a relatively strong linear relationship between these two variables. So introductory college course average and upper level college course average have a very strong linear positive relationship. We need to be careful because, as we've said before, the correlation coefficient can only be interpreted as the measure of the strength of a linear relationship. So, in order to do this, we're going to need to look at the scatter plot so that we can verify that the relationship is indeed linear to begin with. Otherwise, we can't use that correlation coefficient to say anything about the strength of the relationship. So let's take a look at some properties of R that we're going to need to keep in mind. Number one, the correlation does not change when the units of measurement of either one of the variables change. In other words, if we change the unit of measurement of the explanatory variable and or the response variable, this is going to have no effect on the correlation coefficient R. Here is an example of that. We've got a couple of graphs here. Both of these are measuring as our explanatory variable the age of a driver in years. And here in the top one, we're looking at how far away a driver of a particular age can read a sign in terms of feet. So here's 300 feet, 400 feet, and so on. Over here, we're measuring how far they can read the sign at a given age in terms of meters, how far away in meters. So we're changing the units for the two graphs, but if we were to run the calculation through StatCrunch and ask it to give us a correlation coefficient, we would see that they're exactly the same. You can see here we still have a form that's linear. Okay, so we see basically a line that these data seem to cut through. The direction is negative because now we have decreasing y values as x gets larger. And the strength of the relationship, because this is in absolute value close to 1, or another way to think about it is this value is closer to -1 than it is close to 0, tells us that the strength of this negative linear relationship is relatively high. It's a relatively strong relationship. It's not as strong as 0.93 that we saw in the previous example, but it's still a relatively strong linear relationship. So that's our first property, it's unitless. Second, the correlation only measures the strength of a linear relationship between two variables. So it's going to ignore any other type of relationship, no matter how strong that relationship is. We've said this before, and this is the common error that we talked about that students often make. And this is a point that really needs to be carefully pondered. Here's an example. Let's suppose we look at the relationship between two variables, speed and fuel used, how fast a vehicle goes and how much fuel that it uses. So the average fuel usage of driving a fixed distance in a car and the speed at which the car drives. Now, if you look at these data, you can see that they definitely follow a curvilinear pattern. This is not a set of data that has a linear form. Therefore, we cannot use the correlation coefficient to describe the strength of this relationship. Now, you can compute it. You can tell StatCrunch or Excel or a scientific calculator to compute the value of R. It will do it because you tell it to. But this correlation coefficient is not going to be valid. It's not going to be valid to use this to interpret anything. So be very careful as you make your way through your data sets. You need to look at the data. You need to see it's linear. If it is linear, then you can go ahead and compute the value of R and use it to interpret the strength of the relationship. So that's our second property. It's for linear relationships only. It's also unitless. Third property says that the correlation by itself is not enough to determine whether or not a relationship is linear. You always need to look at the data. So you might have a correlation value that looks very good, so to speak, but it's not going to tell you whether or not the relationship is linear. Here's an example of this, right? If you were to compute the correlation coefficient of this set of data, it's relatively high. If this data were linear, it would tell you you had a relatively strong linear relationship. However, when you look at the data set, you can actually see that you don't have a linear relationship. You don't have a linear form. You probably have a curvilinear form here. So just looking at this value here of R being very close to 1 doesn't tell you the actual form of the data. So be careful there. So we've seen a couple of examples. In this case, we have curvilinear, yet R is close to 1. Back up here, in this previous example, we saw curvilinear, but R wasn't at all close to 1 or -1. So again, the moral of the story is you've got to make sure that you actually look at the data. And then finally, fourth, the correlation value is heavily influenced by outliers. In a previous video, we talked about how important it is to look at your scatter plot and see if you have any outliers that might be tainting your data, so to speak. Here's an example of a data set where we go ahead and we compute the correlation coefficient and we keep the outlier. So this is a data set that measures for different animals their gestation period and their longevity of life. And you can see here the data here include what appears to be an outlier over here for elephants. Right? So elephants live for a very long period of time, and their gestation period is also very high. Overall, you can see the form of the data appears to be linear. The direction appears to be positive or increasing. And so we can go ahead and calculate the correlation coefficient R, and it is 0.6632. So remember, closer to 0 is weaker, closer to 1 or -1 is strong. So we might categorize this as quote unquote moderately strong. So this is a moderately strong positive linear relationship when we include the outlier. Now, if we decide that this outlier should be removed from the data set and analyzed further without it, then we get something like this. So here you can see I've removed the data for elephant, so it's not being computed, and it's not also being graphed, right? And so when we do that, we see that the R value drops. It was 0.6632, it's now down to 0.5190. So you can see that the omission of simply one data point can actually impact your R value quite a bit. So you can probably imagine that it could make it go up very much or it could make it go down. And the point is, look at the data, make sure you identify any outliers, and then make appropriate decisions about whether or not that outlier stays or goes as you do your further analysis. There's generally not, at this level at least, any really good hard and fast rules for that and how you make those decisions, but it's just something, again, to keep in mind. Okay, so that covers this latest topic, rather, on linear relationships, where we focused on the very unique case where the form was, as I said, linear, and we had some very important cautions here about using the correlation coefficient only when you have linear forms and linear relationships. So that wraps it up for this video. We'll see you in the next one.